very kind invitation. Also, thank you very much for turning up. I hope it's not just because of the free lunch. In any case, I don't know how many of you are working on prognostics and health management, but in prognostics and health management, what we care about is on detecting faults in such a rather simple system as a variable wheel. It would be being able to distinguish between having a healthy wheel or having any of the anomalies. But this is not only the only thing that we're interested in. We're normally also interested in being able to distinguish between different fault types, being able to distinguish if it is a flat spot, a crack, or non-roundness in this case. Ultimately, what we're really interested in is to be able to predict how, for example, the non-roundness is evolving over time. And this is what we also call prognostics. And particularly recently, we have been quite lucky that there has been quite a lot of data that has been collected, has become available on the operating conditions, but also on the system health condition as well. And we have seen quite a lot of developments in the field of deep learning, and this has been quite a fast developing, but also quite a flourishing field as well. But if you look into machine learning, kind of the most flourishing field has been really focusing on supervised learning. And in supervised learning, what we really need is to know which patterns we are really interested in. So the algorithms are really good in learning patterns, but we need to tell them what there is to learn. And this is supervision, so we need labels for data. And in the things that we're interested in, faults, and faults are typically quite rare in particularly in safety critical systems. So this is really impossible for us to collect sufficient number of samples to learn from. And this has been one of the challenges that that has been keeping us busy and has been motivating a lot of our research direction. And what is even more difficult is if we have a new system, and if we have a very modern condition monitoring system, and if we wanted to apply machine learning or data-driven algorithms, we do need quite a large data set typically to train our algorithms. And this is could be troubling to tell to the operator that we may need to wait maybe for 1 year or maybe for 2 years until we can really start monitoring something. And this is really not a good solution. So what could be a potential solution? Because typically we don't just have one system. We typically have fleets of systems. Why don't we actually learn or try to transfer between those fleets? And if we think of fleets, this may be something that we may be thinking of. So we would have a lot of similar systems that are operated in a very similar way. And then we could just combine data from them, train, and then apply it to a new system or apply it to a new operating condition. However, in the type of systems that we are typically dealing with, this would be rather the case for our fleets. So they are very heterogeneous. Typically, they would kind of not even do maybe say the very same. They are operated very differently. They would have been taken into operations at different points in time. And sometimes we don't really have big fleets, and if at all, we maybe have two systems that are a bit similar, and then our job would be to try to learn or to transfer between those. And just to summarize what our challenges have been, so we started with missing labels. Labels are samples with faults for us. We also have quite high diversity of operating conditions, and this is irrespective of which systems we're actually looking into. But also what we face is, if we are considering those fleets, is we would have heterogeneous hardware configuration. So they are not really the very same when we are taking them into operation. And we would also have very diverse mission profiles, which would then also define our operating conditions as well. So this is what motivates us to develop algorithms that enable us to really transfer the operational experience, but also the fault patterns between units of a fleet or between different operating conditions that are not the very same. So basically, what we are not looking into is a fleet of systems that are the very same, and we would just combine them and train and plug in. What we're really interested in is these diverse systems where we cannot just combine them, because if we did, then the models would typically fail. And one of the research directions that has been followed in this field, or it has been applied for this type of problems, has been unsupervised domain adaptation. And we are not reinventing the wheel. It has been proposed some time ago in computer vision, and they have kind of very similar problems as we do. Because what they also face is when they train models under very controlled environments, and then when they when they want to apply it under other uncontrolled environments, typically the performance drops. And this has been encountered really in many different applications. And one other example of that would be autonomous driving. If a model was trained under very nice weather conditions and then it starts raining or snowing and the model hasn't seen it before, then again the performance drops and the objects do not get detected. And that's the setup that we will be looking into. So what we usually have would be this labeled source domain. This is what, so the two terms that I will be using is the source domain and the target domain. And the source domain would be the data set for which we have labels. And what we then assume is that we have another data set that was collected under slightly different conditions or under different conditions, but it does not have any labels at all. So this is really the condition that we set it up with, that we don't have any labels on the target domain. And if we just use this classifier that we trained on the source data set and then apply it to the target data set, as you see, the performance would really drop quite significantly. And what domain adaptation has been, or the domain adaptation algorithms have been proposed for is to adjust those or to align those two domains so that we really can apply the knowledge or benefit from the labels that we have from the source data set and transfer it to the target data set. And for us, domains would be either different operating conditions or different units of the fleet. So this is up to us to define it and how we actually transfer. And at the very first step, we will just take a look into kind of very basic setup. And here we are assuming that we have an experience unit that has all the different fault types, and we would like now to apply it to a new unit or a new operating condition. So that's the simplest setups that we'll start with. And those of you who are familiar with machine learning, what has been really one of the emerging fields has been generative models. And part of the generative models are relying on the adversarial training. And the basic idea of adversarial training is that there is a model that we would like to develop, and this model tries to generate samples that resemble the real data. And that's the goal of our generator. And then there is the discriminator, the detective, and the detective is kind of trying to distinguish, is it really a real sample or is it a fake sample? So that's the two actors that we have. On one hand, we have the generator. On the other hand, we have the discriminator, so the detective who is trying to distinguish them. And as has been shown, so at the convergence point, the generator wins, and the detective is basically not able to distinguish between real and fake images or any fake samples. And this very similar concept has been applied in the field of domain adaptation. So the goal there is to make the samples overlap and to make the samples indistinguishable between the two domains. So that's the task. And again, we have kind of the two actors. We have the generator, and the task of the generator is to generate samples that are as close as possible to the source domain so that the source and the target samples cannot be distinguished between each other. And the goal of the discriminator is to distinguish between the two, so to know from which of the domains is it actually original. It's a very similar concept that is applied for domain adaptation. And the best performing algorithm that has been around have been domain adversarial neural networks. And they have actually two parts. On the one hand, they have this classifier, or so we will see where we can also apply it for regression as well. And that's kind of the normal task that we have. So we need to classify, that's the task that needs to be performed. And on the other hand, we have a second part, and this would be our domain classifier. And the task of the domain classifier is to distinguish between the two domains. And then so these two parts are actually trained together. And the trick that was proposed in this paper in 2015 is just to flip the gradient. Because we are flipping the gradient for this part of the loss, because here we would actually need to maximize it. So then if we flip the loss, we are then minimizing it. And then we can train it together at the convergence, the two domains become indistinguishable. So that's the basic concept. To make domains overlap in the feature space so that we can really transfer the labels or the knowledge on the labels from the source data. And we will come back to this concept several times. So let's start with the application to fault diagnostics. So the setup that we are facing is we have a source data set, shows that we operate a condition or a unit of a fleet. And it's fully labeled. So we know all the faults and we have a labeled data set. And now we have a new data set. And here what we're assuming is that in this data set, all the fault types that are present in the source are also present in the target. But they are not labeled. And the goal is to have a model that is able to classify for us between the different fault types. And there is a domain shift that has occurred. So if we now apply this concept of domain adversarial neural networks and then try to transfer it, the goal would be to have a model that is classifying well on the source and also on the target, and then is able to provide us good diagnostics results. So we evaluated this concept on the CWRU data set that has been really very widely used for cross-domain adaptation. It has 10 different classes, one healthy class, and 9 different fault classes. There are 3 different fault types, and for each fault type, there are 3 different severity levels. In total, it's a 10-class classification problem. And in this, there were 4 different loads, which are considered to be the domains. And the task here was really to transfer in all the directions between all the different domains. And what you see here is the average results of all their possible combinations. And the baseline is, so the baseline would be if we just train on the source and apply it on the target. Train it on one load and then apply it to another. And as you see, the resulting in 95% accuracy, which also tells that the domain gap is actually not so large because 95% is already quite a high performance. But if we now apply this, the domain adaptation to it, what we see is that it improves by 4%, which is still quite significant. So this was the basic case. But this is rather unrealistic conditions, because what we're actually assuming is that when we're developing the model on the target data set, that we already have all the fault type that are possible. And really, this is not the setup that we are typically facing. So this is kind of our basic setup. But what we are rather facing is that, so we have the source data set with all the fault types. We have the target data set that is not labeled, but still contains all the fault types. And we would like to apply it later on to classify all the different fault types as well. And if you look into literature, what has been developed and the setup that they were following is, so it's referred to partial domain adaptation because the target data set may not have all the classes available during training. But what they actually developed was, so on the one hand, they're assuming that on the source data set, they have all the different classes. But on the target data set, they have a subset of classes that we have on the source. But later on, what they would be interested in is only in the classes that were present in the target data set when the model was developed. And this would be just a subset of faults. So basically, only those faults that were present during the model development can also be detected later on. But this is not what we are interested in. or the real conditions. What we are rather interested with the real setup that we face is that in the target domain, when we're developing the model, there may be some faults, but maybe also not. But later on, when we apply it, we would still like to be able to apply it to all the possible fault types. And the extreme setup is that when we're developing the model, there may be just healthy conditions. And this is kind of really the realistic case. We're developing a model, we only have collected healthy data, but we would like to make it prepared to all the different fault types that may be occurring. So that's the setup. We still have the source data set where we assume where all the fault types are present, but then when we're developing the model, we assume that only healthy data is available and no faulty data. But then later on, when we're evaluating it, later on during the application, during the deployment, we would like to be able to classify all the different fault types correctly. So we know that domain adversarial neural networks perform quite well. And when we actually apply it, we don't have all the different classes when we develop it. What we really see is that the latent space actually gets distorted because there is very little information from the target, and then it's very difficult to know where it should be aligned actually. So within this work we then proposed was, so instead of this bilateral alignment, when we try to push the two distributions to be aligned in the feature space, what we propose is to rather preserve this the representation on the source domain and then unilaterally align the distribution of the source of the target domain to the source domain. So that would be the setup that we propose, because we know that the source domain contains all the classes, all the different fault types. We impose that it should be preserved, and that only the target domain is then aligned unilaterally to the source domain. And the way we do it, we actually impose one additional loss, that the consistency loss that enables us then to preserve the representation that we learned from the source domain. So we first pre-train our model based on the source data set, and then we freeze it, and then what we then do is to impose an additional consistency loss to penalize the deviation from the representation that we learned from the source domain. And the two other lost parts are still the very same that we had. We still have the domain discrimination loss, and we still have the normal classification loss. So now we just have 3 parts instead of the 2 parts in the loss that we had before. So let's take a look what now happens. So this was the baseline that we had before, and it doesn't change because we trained it on the source data set, we applied it on the target, nothing changed. But now with this unilateral alignment, what we're able to achieve is still an improvement of 3%. So if you remember, we were able to achieve 99% before, so it's a 1% performance drop, but it's still, if we consider how much less information we have now, it's still quite a good improvement. So this was the problem that we now solved, that we have only healthy data available on the target data set, but we are still assuming that we have this very experienced unit that contains all the different fault types. But again, this is actually not quite realistic. What we typically may be facing is the case that we have one unit that has obviously healthy part, but also maybe some faults. And we maybe have another unit that again has a healthy part and maybe some other faults. In the extreme case, they only overlap in the healthy condition, don't overlap with the fault conditions. But we may have any other combinations as well. And this would be the more realistic setup. But again, later on, we would be interested to be able to apply it on the source unit, but also on the target unit. So now we need actually to evaluate it on both the source and the target. Let's take a look how we could actually approach it. And the idea that we followed here, so it's not, it's a bit different way that we have taken here. And the idea that we had, we could actually generate faults. We could try to use the generative models to generate faults for us. So we tried to follow, not this idea of generating faults, but not from the perspective of generating samples that would resemble the domain, but really rather to generate faulty samples without having seen them. And typically, GUNs have been performing actually quite well, or any derivation from them. And if you look, they actually look quite realistic, but usually it's still, well, it's getting better and better, but often still possible to spot the fake images. And one of the things that they're not getting quite right yet is symmetry. What you see here is that, so it's really not symmetric. And again, here it's not symmetric, and here it's not symmetric. So it's still possible to catch it. But for us, what we are interested in is actually to still be able to preserve the physical interpretability. And it's not just generating images, and when we look at the images, we are still able to spot it. But what we should be able to spot is also the deviations from the physical conditions. And this is rather more difficult. But also we need to be consistent with the operating conditions and to be able to really replicate the real fault behavior. So that was the starting point of where we started off with the challenge that we took, and the general idea that we followed. It was applicable for this type of data sets, for this type of data. What we actually assumed was that for a fault sample, that we should be able to separate between the healthy and the faulty part. And that is the basic assumption that we actually saw. And the assumption would be that the healthy part would be domain specific, but that the fault patterns would be domain independent. If we are able to do that, then we can really add it up and then mix the healthy with the faulty conditions. And this is the hypothesis that we took, that in the Fourier domains, in the Fourier we assume that the Fourier spectrum can be subdivided into parts, and the first part would be the part of that represents the domain-specific healthy conditions, and the second part would be representing domain-independent faulty conditions. And this was the assumption that we based our work on, and we also put a weight factor in it that would enable us to scale the fault pattern. So basically, it's healthy. So and the other assumption is that in the Fourier domain we can actually sum them up. So that's quite a strong assumption, but that's an assumption that we made, and we can see how far we came with it. So that's what we follow. And if we make this assumption, we are still assuming that we don't have any data in the target domain. So basically, we cannot train on the data in the target domain because we don't have any faults. But because we have faults in the source domain, we can actually train our model to generate faulty samples in the source domain. Since we made this assumption that we only need to train the generator to generate this default pattern. So this domain-independent part, the fault pattern. And then we can then add this the healthy samples, and once we added the healthy samples, then it should become a real signal, a real faulty signal. So that was the setup that we made based on the assumption that we made again. So we are training our generator to generate fault in domain-independent fault patterns in the Fourier domain. And then once it is trained, then we are adding up the healthy samples, and this provides us the faulty samples that we can then pass through our or provide to our discriminator, and the discriminator is then supposed to tell us is it faulty or is it fake or is it real. So we still have so on the one hand we train the models for each of the fault types independently. So now we would have 3 different models. But then we also, because the fault types have different severities, we then had here the sampling from the different severities that enabled us then also to have samples that would be representing the different severities as well. So we trained the model based Wasserstein gun, and then after convergence, when it's straight, what we then can actually do is just apply it and then generate our faulty samples. And then we can plug in our target, our healthy target data, and then we can sum them up, and then this would be our faulty samples, and then we can train our model with that, because we know that because we are generating the labels, we also know which labels it is to train. So that's the procedure that we do. We first train it to generate fault signatures, that's how we call it. And then once we train it, we just plug in any healthy target data, and with that we are able to generate fault samples. By the way, if you have questions, please feel free to interrupt. So this time we worked with a bit different data set. It's also a benchmark data set. Was collected by Paderborn University. Has also 4 different domains. It has also been applied quite a lot for domain adaptation within different working conditions, and has different torque and different rotational speed. Actually, domain 1 has been behaving a bit differently to all the others, so this was the more difficult one. By the way, what we're assuming here is that we have on the real or on the source data set, we have healthy samples, and then we have only one fault type, and this will be the inner ring with 3 different severity levels. And for the target data set, we have outer ring fault with 2 different severity levels. So they are not overlapping in their fault types. The only thing that they are overlapping with is on the healthy data set. And now we are generating those synthetic data, so the outer ring fault for the source data set and the inner ring fault for the target data set. Once we have them, we are evaluating them on the 2 real data sets that we have made. Let's take a look how it behaves. So what we have as the baseline here is, because the data set is more difficult, the baseline we have 83%, and this is a mean over the 2 different data sets. At least in this evaluation, we excluded this operating condition that behave differently, but in the paper we compare all of them. And if we apply this fault signature gun, that's how we call it, we're able to improve the performance now quite significantly to 96% for the classification, which is quite a nice improvement. And we also wanted to see how realistic those fault patterns would be that we actually generated, because this is what we started with, and that we would like to have fault patterns that are really replicating the real conditions. So what you see here is that I think it's a mean over 100 samples, just to show how it behaves. So the blue one would be the synthetic fault, the synthetic data set. The green one is the target data set. And the orange one is the real source data set. As you see, the real source data set and the real target data set deviate actually quite a lot. But the synthetic target data, the synthetic data set is really replicating the target data set actually quite nicely. And we also took the difference between, on the one hand, the real data set and the generated, the synthetic data set, but also the real target data set and the source data set. And, you see in red the difference to the synthetic, and at the bottom it's just flipped on the difference between the target and the source. And what you see is that actually the generated samples replicate the behavior quite nicely. They did not catch it this part that well. But if we just if we would be just applying the source data set to the target, this would be the difference. And it's really not following the very same patterns. So it seems to have captured it quite nicely. They're still not. So that was for diagnostics, and I was actually at the beginning not planning to touch prognostics, but Marcia asked me to touch prognostics as well, and these are actually quite recent results that we have. So how about prognostics, and how can we apply domain adaptation to prognostics? So how about applying, using the very same concept? So this is what we again started with, and this time we looked into the new CMAPS dataset. Was collected in collaboration with NASA and the turbofan engines, and it contains different light classes. So it has full degradation trajectories within different flight classes, and flight classes are short, medium, and long flights. And if you look into how the degradation patterns actually behave in these three different flight classes, now you see just 2 units per class. So the blue ones are the short flights, the orange ones are the medium, and the green ones are long. And this line would be the point of time when the fault has actually initiated. And what you see here is that they really have quite different end of lives, and they behave really quite differently. So if we train a model on short flights and applied it to long flights, it would not, the performance would not be that good. And that's also what we see in, this is just for the scenario descriptors, just the distribution that you see here. This is on the altitude and the Mach number, the throttle resolver angle, and the temperature, the fan inlet. So the distributions are really quite similar. So just as a reminder, this was the architecture that we saw before, the domain adversarial neural networks. And now what we could actually do, so it's not really made for regression. Normally it's really made for classification. But at least in this case, we applied it still for regression. And then we could still leave this domain discriminator, and then what we would need to plug in is now the regression part. So we just need to change the loss here. But if you look into what the challenge that we're actually facing is, if you wanted to train our models short flights and then to apply it to long flights, there is actually quite some discrepancy between these different parts of the operating conditions, particularly the duration is also quite different. And this is what the algorithms will be struggling with, because some of the parts of the flight will be very much represented in one data set, but not in the other. This may really result in a misalignment when we try to do it. So then the idea was to try to take this information on the operating conditions into account when we align the model, so when we develop the model. The first idea, we could just distinguish between the different operating conditions and then train the models independently for the operating conditions. So distinguishing between takeoff, cruise, and landing. So that was one of the considerations, but as you see, it's actually not always very representative to just divide it in this way. So then what we decided to do is to just subdivide it based on the first order derivative of the altitude. And now we would not be distinguishing between takeoff, cruise, and landing, but rather between ascent, steady, and descent. These were the three conditions that we decided to distinguish based on this on the derivative. This will be now the different colors that you see now would be the three conditions that we distinguish. And the idea would be to develop models for each of them independently, and then to apply the transfer between. And this is again just a distribution to show you for the different flight classes how it actually looks like. This would be the blue one is the ascending, the brown one would be the steady condition, and the green one would be the descending part. And as you see, there is quite some differences between the different flight types. It's just a snippet of the different conditions. So how can we take care of it? And the simplest idea would be to use the very same architecture, but to use the very same architecture for the different operating conditions independently. So to train it three times for the three conditions. So we still have this domain discriminator here, we still have the regressor, but before we're distinguishing between the three operating conditions, and then we are training them. So this is what we call operation profile specific domain adversarial networks. And we call it hard because we're really distinguishing. This point would be belonging just to ascending, this one would belonging just to descending, and this one would belonging just to steady profile. And the other direction that we followed a bit was kind of to have a soft assignment, because it may not always be for sure. So that's why we may have a regressor model, and then we would just assign. That's the soft assignment. So what we then applied, as mentioned, we defined this domain adaptation task between short flight conditions and longer flight conditions. So that's how we transferred it. So between short and long, this would be one task. Between short and medium, between medium and long. Because in the other direction, long contains all the operating conditions. It's already behaving quite well. And the baseline is again just trained on this domain and then apply it to the other domain without any adaptation. So this is the RMSE value that we have. We also applied the NASA score, but it's I'm not presenting here. And we applied several other domain adaptation tasks through. This would be kind of one of the simplest one would be adaptive batch normalization. This is multi-kernel MMD. This is the standard DAN that we applied. These are the two parts that we proposed. So as you see here, it actually improves. Other BN is not performing that well, but here the others actually are already performing and improving the performance. And the two architectures that we proposed are behaving quite similar. And also, as you see, the domain gap actually decreases. So this is the largest domain gap that we saw, because this is the largest difference. Between short and medium, the difference is already quite smaller. Between medium and large, it's really even decreasing the performance. We had 1/3 that we proposed, and actually the third one was performing the best between M and L. Surprisingly, it was improving a bit, but I left it here. So just for the conclusions, what I was showing you that we were able to transfer the operational experience for the very different setups in the increasing complexity levels, but also for the different tasks between diagnostics and prognostics as well. And this is what may enable us really to start monitoring the systems from quite early stage. Because this is where we will already be able to transfer between operating conditions and to perform there.